Good morning, afternoon, evening, everyone, depending on wherever you are in the world. I would like to welcome you all to today's lecture. I'm very much looking forward to it. I would like to welcome Dr. Kawai Kwok and thank him for agreeing to give this lecture. Kawai's research interest lies in the areas of mechanics of thin structures, stimulus responsive materials, and architectures. His current research focuses on understanding and harnessing instability and localization of ultrathin composites and polymer membranes to design novel shape reconfigurable structures for aerospace applications. He received his PhD and Master of Science degrees in aeronautics from Caltech. And prior to joining the University of Central Florida in 2017, he was a research scientist at the Technical University of Denmark. He is the recipient of the NASA RHG Exceptional Achievement for Engineering Award. Kawai's research is supported by NASA, ONR, and the industry. I'm very much looking forward to it. I mean, I called him Kawai because he's Dr. Kawai Kwok, but Kawai and me studied together back like more than a decade ago at Caltech. So I've been known him also on a personal as a level. So I'm very much looking forward to your lecture, Kawai. Looking forward to it. Thank you very much for joining us, and the stage is yours.
Yeah, well, thank you, AJ, for the introduction. Yeah, seeing you and reminded me of the time at Caltech, where we were spending the whole night just finishing all the homework, which are incredibly difficult, probably the most difficult work I've done in my life. But that was very good and nice time there. Thank you for the introduction and the invitation to this, time. I can share some of the research I'm going to, we've been working on in Florida. And so I give the topic, mechanics, materials, architectures for large shape reconfigurable structures. It might be a little broad title for today's talk, but it kind of captures of the overarching theme that we're trying to work on at the University of Central Florida. But today I'm going to talk about, I'm going to pick, one or two projects that that I'll specifically talk about. And so, let me start by, telling you a little bit about, the overall, research themes that we are, working on in our lab. So our lab is structures, materials, design laboratory, and it's centered around really, fundamentally on a few areas in mechanics. And there are really the core of what we do fundamentally. We use a combination of computational, experimental, and also some fabrication techniques and try to understand some of these fundamentals. And these three areas are, thin shell, thin membrane structures that, these are very thin, structural forms that, have very interesting properties such as instabilities, which we can leverage to make, to design deployable structures, for example. And the other two areas, one of them that we work on quite a bit, right, recently is to look at the microscale and the mesoscale architectures inside the materials. So obviously composite is one of them that, you have an architecture that let's say you have carbon fibers and that, they go in different directions inside the material and you can control them nowadays pretty well. And so that is a sort of a mesoscale architecture. We also dive into carbon nanotubes, as a functional material inside composite. And in there, there's a microstructure that is, the heart of, the functionality of the material. And one very another core part of that theme that we're working on is material viscoelasticity and viscoplasticity. So mostly really polymer materials that we've been working on. And that is, there's, several purposes for that. One of them is more engineering emphasis where we like to understand how material polymer materials, change over time, and they're very time-dependent materials. And that has implications for long-term applications. And there are a lot of, a lot of aerospace applications, they run for a long period of time. So that is one of the motivation we started on that. But also polymer materials, if you look at the time dependence, you can actually leverage that as a way of making new materials, because they change stiffness over time. So you can actually look at that in a way of thinking about that as a variable stiffness material, which you can control that by temperature. And but these three areas, they're not really isolated. What we work on and the applications and problems that we apply them to really are interactions of these few different areas. So I'm going to kind of go through some of the problems that we are working on, kind of to show you how that relates to mechanics. And then we'll talk about particularly one or two of these projects that we work on. Now, for example, deployable structures, we use composite, very thin composite materials. And so obviously there are architectures inside that we use to control and to optimize stiffness. And there's instability of that thin composite is the principle of folding and making deployable structures. And so that is definitely a combination of the architectures, the instability of a thin shell. And on top of that, we're actually looking at how that polymer viscoelasticity is affecting the actual application. So this is deployable spacecraft. This is a picture of just a reflector, prototype that we worked on some years ago. It's a parabolic shape when deployed, and we have a concept that try to fold it in several ways. One of them is to kind of reduce the radius, and then it's going to go in another spiral folding. So it has some a lot of applications and a lot of interest to make larger spacecraft structures, and therefore deployable is one of the main still one of the very efficient way of doing that. So on the right hand side, let me go over here. This is a new project that we started very recently, and it's to think about the deployable propeller blade. So the idea, the motivation there is that if you look at very large propeller or rotor engine, the limitation of on the efficiency is going to be the bypass ratio. So bypass ratio is the amount of kind of flow around a turbo engine that does not go through the actual combustion core. And that the efficiency can be increased if you can increase the blade length really. And so some of these smaller type of turbo engines, they're the bypass ratio is pretty small, and that's because they have to keep around a diameter, overall diameter of the rotor, sorry, of the engine, because of the physical dimension. So there's a project that we're working with the Office of Naval Research just to look at how we actually can we make a deployable blade that once it's deployed in air, it extends its blade length, and so the efficiency can be increased for long range missions. So it's quite a challenging project. So we just got started, but using quite a lot of the ideas that we have been thinking about for the spacecraft realm, but then now applying it to a new problem. So and there are a few other areas that we work on. One area that we are kind of coming up with is more of a material idea. Is that well, we have we can take a look at material that has all this time-dependent properties, and they can be actually the time scale of the material can be increased and decreased by temperature. And so in that way, you can think about, well, I can look at it as really a variable stiffness material. And one of that, good example of that type of polymer is actually shape memory polymer. So all the shape memory polymer, besides that, they have this, you can think about the shape changes and the shape, fixation as just a time-dependent phenomena. And obviously, we have to think about a way to impose the heat so that we can do the actuation. And in that particular project that we are thinking to use is actually a carbon nanotube material, which is, can be infused into the polymer, making it actually conductive, so we can electrically heat it up. And other nice benefit of that is actually the carbon nanotube has a sort of a piezoresistive behavior. And you can utilize it as a strain sensor. So basically, you get the strain sensing and the shape actuation by combining the two different properties together on a composite. And so we call it integrated sensing and actuation. So there's quite a lot of electro-thermomechanical coupling, and we'll talk a bit more about that later on. And ultra-thin composites, another area that we have worked on it quite a bit. It's also related to deployable structures because we use this very thin composite materials to increase the folding curvature for various deployable structures. So if you look at deployable structures that it requires some amount of folding and rolling or curving of the structure, so just thinking about the take the beam theory, right? That the curvature increases if you can reduce the thickness, and then the only thing that is in the way is the maximum failure strain. So that is a material thing. So if you can increase that as well, reduce the thickness, then the curvature of the achievable is going to increase. And that is a technology that has came out from the industry, but it becomes quite a lot of different mechanical behavior coming out from because of the very thin layer, and also the sort of architectures inside now play an even more important role. Finally, a superpressure balloon project that we've been working a bit, mostly on the material side. This is a huge balloon that you can see that several mostly carry out by NASA, and it's a way of getting to the upper atmosphere very quickly and for a very long time. So without launching. So this is a low-cost way of getting to a high enough altitude and allows you to do quite a lot of different types of measurements. And sometimes you can even look at the space from a high altitude. So this is a huge balloon structure, mainly made of a common polyethylene material, extremely high, extremely viscoelastic material, so it varies very easily over time, and there is a lot of complex modeling that comes into looking at this balloon and modeling this to ensure that the long-term flight is reliable. So this is sort of an overview of the kind of different areas that we're moving on to, and you can see that all of these actually relates to the size of the structure. All the structures and problems that we work with have this common trait that the areas or the volume are large, and so there are a few if we summarize that there are a few purposes or the reasons for that is because, well, in space you want to harness the electromagnetic spectrum. All right, so this is the making antennas and telescopes, trying to, manipulate that spectrum. And if you have a larger area in space, then you can obviously get a lot better signal, right? And that is, why they should be large. And also, if, solar arrays and solar sails, these are very also are quite straightforward why they should be large, right? Your large arrays get you more solar energy, right? You can have more area span, and that converts more solar energy. Solar radiation pressure, is a propulsion. If you have a larger area, you can get a higher propulsion force. So it allows you to get some, nice thrust in space for free. And the last two bullets is the harness pulse buoyancy, and that is more on the volume, right? That is, you have a higher volume, then you can have a higher lifting force, and that relates to the balloons that we talk about. The aerodynamic pressure, that is the rotor engines. Again, if you have a lifting surface that is large, again, you have more capability to change the design. Either it can be engine or the propeller. All of these applications, or most of the applications, are more focused on aerospace, and the challenge is quite one of the challenges quite common is, how do we launch it, and how do we deliver that such large structures into the environment that they should operate. So they're not operating all the time. So they need to operate in space, for example, in antennas and telescopes, but they are made on Earth, right? So there's a problem of delivering that or transferring that to their site. And the same thing with the engines. So they only need to work in air, right? But they obviously you need to launch it from ground. And there are various ways of doing that. In some ways are very limiting in terms of the physical dimensions. Some of these aircraft are launched from cylindrical tubes, and so you can't actually have a very large rotor engine because the launcher is very limiting in terms of space. So there are these limitations we try to overcome by having structure that can change the shape. So and therefore the name reconfigurable structures that they can change the shape so that they reside in certain structure, certain physical constraints, but then it get into its large operational shape, automatically. And how do we design such a structure reliably? We want it to be also volume efficient, mass efficient. So how do we do that? We center around several materials and architectures and the geometry. We try to study and combine those things and see if we can have a little and try to come up with concepts that can increase the performance of these things. And the projects that I like to talk about, right, there are two of them that I want to specifically talk about, and these are more recent work that we've done. So I feel more excited to share about those than the others. The first one is thin ply composite laminates and how we model that and try to understand the behavior and how we use that in looking at deployable spacecraft booms. The second one is the integrated sensing and actuation material that we're developing, and based on this shape memory polymer and also a carbon nanotube material. So I like to spend a little bit more time on this one, mostly on the first one and some of it on the second topic, and most of them are centered more around the the materials and architectures for making the structures. So the first topic, thin ply composite laminates. So just a little bit of background on that. Thin ply composites. So these are composites that are much thinner than traditional composites, and this is enabled by a process that's called a spreading process. So you have normally toes in a composite that are larger, right? And that contains a lot of fibers in a toe. And typically they are sort of teardrop shape, and they're have a does not have very high aspect ratio. So, but there is a technique that spreads out these toes, and then the end product is a spread toe of carbon fibers. And now the aspect ratio is a lot higher. So if we take a look at kind of the difference between the resulting composites, so we have on the left hand side, this is just a traditional composite. The toe is circled by the yellow ellipse, and that is the original one. But in a thin ply composite, it's really thin. That the same amount of fibers now are being stretched out, and so it becomes really flat. So the idea of that is that you can really compress the thickness of that final composite. And again, the idea of that is to use that small thickness to achieve high floating curvature. And obviously so we work on there are some examples of what actually use composites in space. So they're just I'm just taking this from the literature. There are antennas, and then there's the ROSA, which is a solar array structure that is deployed by two booms that are made of this composite. And the orbiter is a type of a sailcraft in space that you can use it to deorbit things in the orbit that you don't want it to be in the orbit anymore. So a lot of them are using composites now in spacecraft structures, and obviously in particular deployable spacecraft structures. Now, all of these have one of the example that we actually work very closely with at the moment is with NASA, and this is one of the missions they are working on. Is a new design on a solar sail system. They call it Advanced Composite Space Solar Sail System, and basically it's a solar sail, and there are 4 booms in the middle, in the center, and that goes like a cross. And then you have a sail, which is a very thin membrane that is being stretched out and deployed by the boom. So the booms are kind of structural support for that sail, and they intend to use this as having it as a sail mission to I think look at asteroids and a little bit farther out in the space without propulsion, without propeller. And the booms that used to support that structure is one of the geometry looks like that. It is looks like a an omega shape that is make out of thin ply composite booms. You can roll it up, and then eventually it's kind of all stored inside a mechanism within the satellite, and that is how the whole thing is put together. Now, there's something about the mechanics of that, that shape of the boom, right? So it looks like, you can see from the previous slide, it's really more like an omega shape, and it's really, manufactured from 2 pieces. 2 pieces open, a cylindrical type thin shell structure. And this has been studied many years. So it's a building block, has been used very intensively in the deployable space community. Has been around for many years. Obviously, they were not composites back in when they first came out, but they are increasingly made from composites now. So just a little bit about the kind of fundamental principles, so we kind of understand how this works. Is that, well, basically the mechanic principle behind this is a snapping instability. So if you kind of take a tape spring, you will notice that if you bend it, suddenly it goes from uniform bending into a local buckling. And once you get into local buckling, the buckle actually stays with the same radius. It doesn't change anymore. It can move around, but it is a state that is a localized buckle, right? And if you take a look at the moment rotation diagram of that, basically the behavior is that you have uniform bending and then you snap it, and the load drops significantly, and you have a local buckle. And so this is a very nice behavior to exploit, because you have a large, you really want to take a look at that regime, that you have an increase in rotation. That means a large shape change, but then what you need to do is, very, very small moment that you need to provide. So this is, a great way to make a deployable structure, because the loading applied and the deformation or the shape change you get is not proportional to the loading applied, right? The loading, is always low. So the snapping instability is really the thing that behind all this work. However, there's another issue with composite, right? So there's pretty nice composite materials that, if you get it thinner, you can even get that curvature higher. So, you can control that buckling load. And you can design various different radius and so on. There's been a lot of studies on that, how to optimize the tape springs, how to deploy it. But one problem that came out because of making it from a composite is the following, which is that is not so prominent when we make a metal tape springs. Is the long-term storage effect. So I worked on this, starting from my PhD. I think that the last year of my PhD, I started working on this, and still it's a relevant problem today. If you roll up if you fold composite structures and keep it in a deformed shape for too long, there is, because of the viscoelasticity of the polymer matrix, the deployment actually becomes, a lot more difficult to handle, and there's some unexpected behaviors. Some of them are not very desired. So there's some examples of that. Sometimes that the deployment actually got stalled in the middle, that you don't have a full deployment. While we expected, that it comes back completely for just an elastic tape spring. So just go back to this real quick, right? On the unloading path, once you release that load, because this is a higher moment, obviously, once go back to a lower energy state, and that will definitely go back if this is elastic, but and it wants to go back instantaneously. But in the case that if your material is viscoelastic, that actually does not come back instantaneously. So there's some creep after deployment. So there's still a recovery that can take a long time, and that is not a good thing for deployable structure, because we like to have this shape, the correct shape, so that we achieve the same stiffness that we designed it to be, and then we want to have the same shape accuracy we like it to be when it's deployed. And also another thing that can happen is that you can actually change the structural behavior entirely, because one of the effects of this elasticity is change the stability landscape of the structure. So tape springs can be made into having different stable configurations, and that have actually worked from Sergio Pellegrino. That was a very pioneering work on that. How you make bistable tape springs, and that was based on the elastic tape springs, and then later on, if we apply that composite to make bistable tape springs, then there's this problem that came up, that sometimes you actually lose the bistability if you stow it for too long. So So what we are trying to do here is can we understand that, and can we be able to model that composite material, so that there's a collaboration with NASA, mostly to look at the composite rooms in the solar cell system they're designing, and providing the sort of modeling capabilities to them, understanding that try to understand different lamination, and how we can put a number on how that stowage effect on the recovery. So we started with sort of a linear viscoelastic properties, looking at the kind of matrix material and characterizing it. That's really the first step. And so this is a very fundamental thing about viscoelasticity, that you can characterize them at different temperatures, and you can form something called the master curve, or which actually describes the modulus change over time. So this is the experimental data that we obtained in the lab. This is for a particular epoxy that is a candidate for composite materials for that space application. And you describe that relaxation modulus by something called a Kearney series. So you can describe that for a very long time. So obviously we did not do this experiment for this long. So it was actually combined from several different tests at different temperatures. And but then that is only the matrix. So to be able to look at the obviously there are various effects if you incorporate the fibers in different levels, and for the thin ply composites that are being used, they are plain weave woven composites, thin ply composites, and so there are at least two scales of, or two levels of architectures that can happen. The first architecture is the more on the micro scale, and there's just the toe cross section. So there's about 10 fibers, right? 10 carbon fibers. Each one is about 5 microns to 7 microns for the thin ply. So you get some unidirectional, basically type of microstructure, unidirectional composite. But then you go to the next level architecture that's on the mesoscale architecture, that is you see this woven layer, and also if you use more than a ply, then you get even more variation, because each ply, the plain weave pattern, they don't have to match up. So sometimes you have the gaps between different layers, they kind of, there are mismatches between those. In thin ply composites, these things matter a lot more than traditional composites. So we see a lot more variability, so to speak, from kind of, we look at composite to composite in thin ply. The approach that we are following is a kind of two-scale micromechanics approach, and then this is trying to capture the micro and the mesoscale variation of those composite fibers inside the fibers inside the composite. We formulate sort of a viscoelastic plate model. So we take just the Kirchhoff linear plate model, and think about now, if there's a viscoelasticity, what happens? So we kind of reformulate the whole kind of ABD matrix, the composite classical lamination plate theory, but now with the addition of actually describing the variation over time of that composite. So that process actually goes from getting the unit cell on the toe, and then we go to the laminate with including all that geometry, and then go to the final element and carry out that homogenization. So in the end of the day, is to get a constitutive equation that exactly looks like a linear viscoelastic constitutive equation. So And we have to do that at each level. The first level that when we do it, the homogenization or the mechanics of a single toe, then we have to reserve that this is still a three-dimensional continuum. So we describe that unidirectional toe as a 3D continuum with a stiffness matrix that can be all expressed in terms of pony series. So this is just the classical Boltzmann superposition integral for viscoelastic material. So you have the strain, stress, and it's an integral equation over time, right? So this is no longer elastic but viscoelastic, and all of these are described by relaxation modulus tensor. And each of them is going to be a pony series. Which is a series in time that is described by relaxation time. So from the matrix that we characterized experimentally, and now we have the fiber, which is at the moment assumed to be elastic, actually linear elastic, and we can compute this general tensor, which is anisotropic, but they all are time dependent. And taking from that, we can go to the next level because each of these, toe in a plane with now is being described by a time-dependent stiffness matrix C. But what we really want is not to carry all these three-dimensional, constitutive equations all the time because that's going to be very heavy with computation. So what we do is to, do a dimensional reduction. Just like the play theory, and in the end, arriving at a constitutive equation in terms of moments and in plane forces, and that gives us less. And you can describe that with just the ABD matrix again. This is now not elastic but viscoelastic. So all of these terms are pony series. So you can get that purely from the experimental, from the computational simulation. So this is just a picture of what we actually have inside the simulation. This is a plane wave unit cell. There are 4 layers of thin ply composite to make up the total composite. And in this particular case, we are trying to do a bending simulation to get out the bending stiffness. So the D is the bending stiffness, A is the in-plane stretching, B is the coupling between bending and in-plane behavior. We carry out some testing. This is a methodology that is called column bending test. It's been developed, I think, in the community, mostly by very a nice man called Tom Murphy. Been working in that field for a long time. And very inspiring work, creative work over the years. So we are using that, as a way to, do the relaxation test so that we can validate our model. And so this is, this has a few, advantages over, for example, the traditional four-point bending test. And when it comes to thin ply, it's even more, and this elastic property characterization is even more useful because when I did my PhD, I used a four-point bending test, and then as we go to a high temperature, we have to have a thermal chamber that runs around the sample, and a lot of vibration happens, and because the thin ply composites is so thin that all the noises that you generate from that four-point bending test is just going to be very messy and kind of kill all the data from the test because the relaxation typically is not very high. The change in the modulus and stiffness over time, is very prone to noises, and you easily just overshadow that with noises. So, but because the four-point bending test does not have a clamped edge, so a lot of vibration and a lot of noisy data come out. And so this is so that's one reason. The other reason is actually the curvature you can get to. is a lot higher in this test. So basically, the column bending test, and you clamp the materials inside the fixture and you apply the compression force. And because that compression force is actually slightly offset from the sample, you actually create a bending moment. And this is a comparison of the modeling and experiments that we collected and kind of summarized in a paper that should be coming out soon. So we are looking at this is particularly for free-ply plane reef. So M30S is the fibers, that is the matrix that we're looking at, and we did this column bending relaxation test. Basically, we imposed a certain curvature. Fix it for some time. So we'll see that the bending moment will relax over time, and that is what we want to capture because that's what we compute from the mechanics model. We do this at several temperatures again, and then combine them into a master curve, which is what we are showing here for two different scenarios. On the left hand side is the 0-90, right? So the fibers is along the bending direction. On the right-hand side is plus or minus 45, so that is 45 degrees from the bending direction. You're looking at what you're looking at is the moment divided by the imposed curvature and the length of the unit cell or the sample, as a function of time. So in the 0-90 is not a lot of relaxation because it's dominated by fibers. And that is the experimental data is down here, and you see that actually the model actually has quite a bit of overprediction on the when compared with the experiment, and we try to figure that out for quite a bit, and actually we see that on most of the tests we have done. And one of the reasons that we are thinking why this is that there's such a large disagreement is actually on the fiber. That our assumption of linear elasticity and symmetric tension and compression properties is actually not a very good assumption. There's a recent paper that talks about a neutral axis shift and carbon fibers that if you look at all the carbon fibers and look at the tension and the compression behavior, they're actually quite different. The compression, response being weaker, so less stiff. But however, in our model, we did not take into account that fact because our model is just linear elastic, so same in tension and compression. And reason obviously is because the compression test on a carbon fiber is extremely hard to do, so not much data around. And this paper that recently came out from EDH that kind of show that, well, if you have a unidirectional composite and you look at the strain on both sides, you can see that the strain is actually higher in the compressive side than the tension side. So there must be a sort of a neutral axis shift in the and if they're doing that in the fiber direction, right? And so the properties is going to be dominated by the fibers. So right now we're trying to incorporate that sort of tension, compression, asymmetry to kind of correct that behavior. But however, if you look at the time dependence, this is not a bad prediction. That the kind of percentage decrease over time, that is the part that coming from the polymer. So that is kind of okay. And we see that the difference is less if we go to the plus or minus 45, and that makes sense because now the plus or minus 45, in that direction, the contribution from the fibers is less. So we're going to see that there's going to be a less contribution because of that discrepancy of the fiber property that we assume. But still, there's an overprediction when compared to the experiment. But then if you look at time dependence, again, they go down, in a manner that is, consistent with our simulation. So this is, kind of on a laminate level validation and overall behavior. So we went ahead and looked at this composite, and there are some funky behavior as well as we found out along the way. Is that some of these on the left hand side, actually here we are plotting the in-plane relaxation, so we was just stretching, and we're expecting all of these relaxation to go down, right? So relaxation is always, the stiffness always goes down over time. So that's why we call it relaxation. And if we applied in plane stretching of the composite, then the stiffness can go down, should go down. And there are a few papers that also study similar things, and then they sometimes will get an upward going curve over time. And so I thought that was quite counterintuitive. And so we kind of take another look into it. Why that, is that real? Because is it just a kind of a numerical thing, or is that real because of something else? And what we found out is that, well, that really depends on how you arrange your ply configuration. So so A12 is the coupling. So if you stretch in one direction, what is the the coupling stiffness on the transverse direction? So the other two have no problem, but that is the only thing that caught our attention. And we studied that by looking at two different sort of extreme configurations that can happen, right? So there are four layers of thin ply, and they're all in phase. We call them all in phase because all the V pattern they are in sync. And if you look at a different configuration that they're exactly out of sync, then this is the out of phase configuration. And we do not see that upward trending of the the coupling coefficient in the out of phase configuration. And so that is quite interesting to us that by changing the configuration, the ply configuration, actually you get sort of different behavior in coupling. And the reason for that is geometric nonlinearity, because if you have all ply playing with ply, having them in phase, and then you stretch it, so all the width is going to deform in the same way all through the thickness, and it's going to squeeze the throws in the transverse direction more, and then they're always reinforcing that that change. So on the left hand side, this is just a deformed shape. I'm just trying to show you, you're going to get an extreme, more extreme curved shape in the transverse direction as you stretch in the loading direction. So that is the case for the in phase configuration. But if you do that on the out of phase configuration laminate, that does not happen just because they exactly cancel out, as you go each along the thickness and each ply, that geometric nonlinearity effect is canceled out, and so it's still a flat laminate. Doesn't matter. So it's really the actual symmetric configuration is actually the out of phase, even though that the plies are all the same in the in phase configuration. And if you look at an axis in the middle, and you don't actually get a mirror symmetry. So because of that, you actually get a much stronger coupling in plane configuration, in plane stretching. And so there obviously in reality there the composite is not either of these extreme configurations, so you get a sort of a random distribution of that. But it seems that the geometric nonlinearity is actually quite a big role inside, and how you arrange the ply actually makes quite a big difference on the property. The other response that we get from it is a localization response. So we take a look at this unit cell model that we have and kind of subject it to a real high curvature and over extended period of time. So we're trying to understand how the in composite, sometimes this thin ply composite, if you roll it around for some time, that it suddenly snaps, it breaks and fails. And it does not fail as you fold it, so it's not elastically, at the failure limit, but you just hold it at some time and it suddenly fails. So it's sort of a time-dependent failure. And so we kind of figured that out, how could that be? Because, it doesn't fail at the beginning. We thought it's going to relax over time, so it can't actually fail because, it should get, the structure should relax and relax more over time, and there's no reason why it should fail. Not the first instant, but sometime later. So that is another, question we had that we thought was interesting. So we subject that to a high curvature and a low curvature for on this unit cell. And so basically the red curve is, normally what we're expecting, where you just, keep relaxing over time and it keeps the shape of uniform banding, indefinitely. However, what we observe is that if you increase that curvature, that fixed curvature, all these, simulations are at a fixed curvature, and we're looking at how that stiffness goes down. And if you go to kind of higher curvatures, you see that at some point in time, there's a drastic drop in the stiffness. And so we kind of look at the deformed shape again for these two cases where we see this kind of a very sudden drop. And we see that there are localization of deformation that does not happen at the beginning, but only happens sometime afterwards, and that's because you have matrix that is concentrated in the region where the matrix is the richest. So you have the plane weave, and in some region there is the matrix, this crossover region where the matrix is the richest, right? So there's proportionally more matrix than the other parts of the structure. And then you get that, more relaxation there. And so over time, all the energy wants to go there because that's easiest to deform. And that is, setting up a localization scenario. And then finally, we thought this might be the reason that, that precedes failure, that, because now you accumulate a lot of strains here and it's going to break here. So we're kind of working on a more extended model because we know that the linear viscoelasticity does not work here at high strain anymore. And also obviously the fiber failure is not incorporated. And this is what we are trying to incorporate in the model now. Right. So we want to take it also to to look at a sort of simulating the actual deployable boom and look at how the coiling and relaxation. And this is an example that we've been working on, for the NASA mission, and just to see how much relaxation we have. So this is still work in progress. So I'm just showing you the coiling simulation. This is the omega boom and the corresponding simulation. Now this has the relaxation homogenization model incorporated. And we're able to get the coiling simulation to go. And what we can get out from that is how much of that, reaction moment at the hub, how that relaxes over time. And this is something we can now predict from our model. So I want to go to the second topic. I know that, I've been talking for some time, but I promise the second topic is not as long. So I'm going to show you some of the idea and also what we are, thinking about in terms of, the next step for this. The integrated shape actuating and strain sensing composite, as I spoke before. So the idea here is, we want to have a, kind of a tightly, miniature thin ply composite where it has, not just stiffness properties, not just foldable, but also we can actuate, and also it has a strain sensing capability. So it has embedded strain sensors. So then we make use of kind of functional materials to achieve that purpose. Now, so we're using this carbon nanotube paper, which is very thin. made up of carbon nanotubes in a mesh, almost like it's very, very compliant. So they're just like a vial of carbon nanotubes. And this is a highly conductive material. And so it's electrical conductive, it's very, heat conductive. We're looking also at a sheet memory polymer, that has this behavior where you can program the shape of the material by going through a mechanical cycle. So obviously, in order to have these two, kind of actuation and sensing together, we kind of have to, combine the capabilities of both things. So what we are getting from the carbon nanotube is actually piezoresistivity, which really means that, well, if you have a strain that is applied on that carbon nanotube, you can see some change in resistance. And that resistance can be related, to, if you put a voltage and measure that, that relates to the strain, so that is strain sensor. But we also use it as a heater when we, incorporate with the shape memory polymer, because all the shape changes is thermally activated. So we can do that. We can achieve both purposes with the composite, with the carbon nanotube. And so this is a simple concept or simple structure that we come up with. We laminate to shape memory polymer, a carbon nanotube paper with two SMP layers. And we can connect that electrically to CNT, and that provides the heating and also the strain sensing. So the problem really is, a coupling between the electromechanical behavior, the thermomechanical behavior, and the electrothermal behavior, right? So you have the carbon nanotubes that would heat up, that would have heat conducted to the shape memory polymer, which can then change shape. That shape converts to some amount of strain that is going to be registered by the CMP. And based on that strain knowledge, one can go ahead and try to control that shape by modulating the temperature. So this is the overall idea we have. We still have not had all the parts working together. We are looking at the shape actuation, and we are looking at the sensing kind of separately right now. But we have been we've gone quite a bit on both ends before we try to put them together. Again, we use a viscoelastic model for simulation, for the shape memory polymer. So you can think about that, the programming shape is almost like, you can think about that, the shape is achieved, it's like a frozen, shape. So that at very low temperature, the polymer actually does not have the time to kind of go back to its original shape. It's in the deformed configuration, it actually wants to go back, but the temperature is so cold for the polymer that it goes there extremely slowly. So it's almost like a programmed shape that is static. And so that's really the principle behind shape memory polymers. But we really like to be able to track that over time, and with all of these properties, the temperature and the force applied and the voltage are changing. Are we able to kind of track that over time precisely? And so we have electrothermal mechanical models, so we have the electrical input, how the heat conducts into the polymer, and we have a mechanical model for the polymer deformation. So this is an experiment we run just in collaboration, in conjunction with the model we are doing. So obviously we want to kind of predict what is the displacement by varying, different sort of programming cycle and both. And so this is the, a page that we, kind of summarize all the results. So on the left-hand side, that is the viscoelastic master curve that we obtain separately from relaxation creep experiments. And you can see that, the modulus, changes very, quite drastically over time. but that temperature, that drastic drop can be, shortened or lengthened by, the temperature of the material. So what really we are trying to leverage here is this is a large change in stiffness that can be, modulated by temperature. So this master curve can be shifted to the left and to the right by increasing or decreasing the temperature. So actually, we can achieve that stiffness in a short time as well if we go to high enough temperatures. So this is on the right hand side is kind of an example that we want to show and demonstrate is we have programming, we go to heat it up, deform the material to a certain shape, keep it there by going down in temperature, freeze it at the same deformation, and then in the final actuation process, we heat it up again with the shape memory, with the carbon nanopaper, and whether we can capture the recovery to the original shape over time. And so you can see that there are simulation, which is the purple curve, and then all the other tests. So this is a exotension experiment, so it's easier to manage. But we have all the thermomechanical interactions incorporated in the model. We're able to capture the actuation pretty well. The only thing that we cannot quite capture exactly is there's still some sort of relaxation, some sort of deformation change when the material is in the frozen stage, the program configuration. So there's, this is related to what I was speaking, that it tries to go back to the original shape you always want to, and it does in some amount. But there are more details on this paper we just published on this idea. So on the sensing side, we are looking at the physical model of the carbon nanotube network. So if you take a look at a carbon nanotube paper, we kind of just stake it on this piece of epoxy and have some kind of conductive leads coming out from there, and so that's going to be our sensor. So this is just a preliminary test we do. We just want to see how much of a sensing capability we get from this, and it's actually quite promising. That we just obtain this paper. There are manufacturers who make papers. They can also be made in different forms and various manners. But you see that the resistance change versus the strain. That is we can go up to we actually went up to even higher strain than 2%. And you can get that pretty sensitive strain response. So this is quite a good strain sensors that we can put on because it's thin. So it's good for a thin ply composite. You can go to high strains without kind of breaking at all. So this is the sort of high deformation, high shape change structures that this would be relevant. But there are a few things about this, strain sensing, the sensitivity or the strain gauge factor of that carbon nanopaper. That is because that sometimes they're not very repeatable, and depending on how the carbon nanotube paper is made. So fundamentally, it's really a network of carbon nanotubes. It's a mesh, and so really there's a lot of microstructure effects going on there. So what we did is, we go in and try to understand, how can we, if we think if we can understand it, maybe we can try to control the microstructure and have some more consistent gauge factor. So this is a stiff model that we come up with. So basically, it's an electromechanical coupling model. So on what we do is that we distribute these carbon nanotubes inside a volume. And then we stretch it. Because of the network deformation, all these carbon nanotubes, which are all conductive, they will change positions. some of them would go out of contact, some of them would, get into contact. So, and that is how the resistance is getting changed, because the distance between these carbon nanotubes, they change as the strain is applied. And so in each of these strain, we can, obtain the positions of all these carbon nanotubes and conduct an electrical simulation. And one of the kind of fundamental mechanisms that governs this conduction of carbon nanotubes is something called the tunneling conduction, right? So the two carbon nanotubes, they don't have to actually in contact to conduct. So there's a very small distance. Once they're in close proximity, they can conduct, and that conduction is called tunneling. And so there are, quantum is sort of a quantum mechanical equation that you can use to model this, and that's what we did. We have incorporated that tunneling conduction, and it's very sensitive to strain, so that once you go out of that tunneling range, you lose conduction, exponentially, and that is a good thing for a sensor, because it means more sensitive strain sensor. This is a work that we just submitted to just look at how our model can we predict that sort of strain piezoresistive response. So on the left hand side is just the total conductivity, and that's the kind of a sanity check on the calculation. So this is the conductivity as a function of the wave fraction, using different sort of size of the RVE, and there's some experimental data performed in the literature. So we kind of compare that with those data, and this shows sort of the expected behavior, that the conductivity goes up, that you hit a certain percolation threshold. So if you don't have enough carbon nanotubes, it does not form a conductive network. So there's no conductivity, that's very low. But once you hit that critical point, and the network is percolating now, and you have a very sudden jump in conductivity. And then, adding more to it will increase it, but it will not increase it a lot more further. So there's a marginal benefit to that. And so that is, you see there are some triangles here. Those are the data points from the literature, and those are in quite a good agreement. But that is of the zero strain conductivity plot, and on the right hand side is really the resistance change versus strain response, and so this is the piezoresistive model. Again, we have two ways of capturing the deformation of the network. And one of them is called the embedded elements, which the carbon nanotube is kind of floating around in that RVE. It follows the matrix deformation. The other is it's called a fiber reorientation model. That is a model that was proposed in the literature some years ago, and has been the main the mainstream model that everybody is using. And that is actually an affine deformation, based on an affine deformation of the network. So there are some different sort of assumptions behind this two kinematics model. So we try to compare that. What we realize is that if you assume that the CNT is rigid, you would not get the right shape of the curve. So that is the case where you have fiber reorientation model, that you assume the CNT is rigid, does not change at all in length, and you're going to get a very different shape and over prediction at small strains. But it kind of gets better afterwards. But if you do use the embedded element without assuming a CNT rigidity, we are able to actually capture the data better all throughout the strain range. So these are the curve that is called the embedded elements, and the circles are experimental data from the literature. So it's quite interesting that there's also related research on that. You can align the direction of the CNT, right? So because this is a random network, so it's the sensing property is actually isotropic. But you know, you can actually control this direction of the CNT at the micro level by applying a magnetic field. There's a nice study at Penn State University. They can make carbon nanotubes to align in a certain direction. And in that way, you can actually control how the sensing properties from you know, by manipulating the architecture. And that's what you know, we're trying to provide a model and understand you know, what is the way forward for that type of sensing. So this is my last slide, and I think I went over time a little bit. I'm sorry, but you know, just to conclude, a few quick summary of that. You know, what I just talked about. That you know, a lot of these advanced materials, and we can make use of. You know, there are micro scale, mesoscale, and nanoscale architectures where they organize, and they actually play an important role in controlling the composite materials. And we can embed and kind of integrate all that different functionalities in a thin ply. I think that is quite a powerful technique, powerful a structure that we are getting. That we're not getting just stiffness. We are getting we're not just getting the stiffness from the carbon fibers. We can get a sort of sensing capability, and if the matrix is something that the viscoelasticity can be taken advantage of, we can actually have a variable stiffness material coming from that. And so looking at the micro and scale architectures and then using these functional lightweight materials, I think that there has quite a lot of possibilities. And to do that, we have computational mechanics models to help us. It allows us to kind of explore the landscape of design and also kind of understand all the fundamentals in these architectures inside the structure. So we have some future directions, several of them. We want to kind of combine all these different functionalities on a thin ply and invoke really dramatic shape configuration. So I've not talked so much about the instability of thin ply. This is another area we have put quite a bit of work on. It's how we can actually induce multi-stability using viscoelasticity and using controllable viscoelasticity to kind of change, get multiple configuration from a thin ply structure. So I think this concludes my talk, and I just want to acknowledge our collaborators along the way. Obviously, a lot of that work, this work, been done by the students in the group, so they deserve the most credit. And we've been supported. Today's work mostly supported by NASA, Langley Research Center, and also the Florida Space Grant Consortium. So this is the end of my talk, and if you have any questions, I'm welcome to answer.
Thank you so much for the really wonderful talk. It's like it was quite detailed and explained a lot of various topics, I think. And I think we can open a forum for any questions. If somebody has any questions, then. Okay, so I see that you have Wembinu as one of the collaborators. Are you using the mechanics of genome approach that Wembinu uses, or?
Yeah, we are collaborating on. So they are trying to use the multi-scale mechanics genome approach to look at the deployable structure. So incorporating viscoelasticity, nonlinear viscoelasticity. So I'll be providing experimental data to them. So the homogenization I talk about is not really multi-scale, and one of the important or interesting things to see is how much of that strain actually happens or appears in the matrix space, and we can't do that with this homogenization. but we are able to do that with multi-scale. So we kind of try to collaborate on using that multi-scale to get out the local strain, which is really important for looking at failure and plasticity that can happen as we fold it. Yeah, so we are collaborating and we're trying to. I personally not using the code. They are developing it more for this sort of applications at the moment. But it's quite computationally heavy. I think that's the obstacle.
Right.
Yeah, this is Hari Krishna. It was a very nice lecture. Just one small doubt. This long-term stress relaxation you are telling, no? Bending relaxation. How much is the contribution from the resin in this property?
Well, it mainly comes from the resin. The carbon fibers are basically elastic, so it does not vary over time. And so the time dependence comes from the matrix predominantly.
So any guess on the how the if we change the modulus of the resin, what variation can be there? Will it be proportional, or you find there every time we need to do this kind of experiment?
Oh yeah, you do have to carry out experiments on new materials because the time dependence is mostly different when you go to different polymers, and that is something that it's a lot heavier than just taking elastic characterization. There are different temperature tests and these are relaxation tests, so it's time consuming, longer term tests that you need to do. And you can always assume a certain amount of similarity between the same class of polymers. Or if you go from epoxy to epoxy, similar glass transition temperature, that might be a good approximation. I think the glass transition temperature is really what you want to look at. If they are similar, then it's a better chance they are about similar in terms of relaxation.
That means if we change the material from bidirectional, that is you have used a BD prepreg. If I change it to a UD prepreg, also if the material resin system is same, we can use the same type of property. Is it right?
Yeah, that is right. Yeah. If the resin is the same, you can use it. Yeah.
Okay, thank you.
Hey, Manu, you want to go ahead? So you talked about a lot of uncertainties in the carbon nanotubes, right? And I mean, in general, there are a lot of uncertainties in there. But did you do anything with regard to that, or is there some kind of a direction that you are looking at in the future to look at how do you quantify these uncertainties in there?
Yeah. So I didn't show it here. So one of we actually looked at two particular kind of variability. One of them is thickness. Actually, that was described in the paper. I didn't show it here. The thickness variation that is quite a main factor. I think it's very hard to control thin film manufacturing to a very uniform thickness, and also from process to process, from batch to batch, the thickness varies, and then that changes the stiffness quite a lot, as you know, from beam theory. So we did do sort of sensitivity study on how what is the range that we can expect from this sort of thickness uncertainty. The other is the fiber volume fraction. That has a much less effect than the thickness. That's what we found. Again, that is not something they can control very well. We get our samples from NASA, and still that is difficult to get consistent volume fraction. But the thickness is a lot more important. I think the ply configuration, we didn't really look at it, and that pertains, I think, more to when we want to look at actual localization and failure. But that is an interesting area that we are trying to look at the moment.
I see. I see. That's interesting. And I mean, when you have these bifurcation analysis that you do, so you showed some of these abacus simulations as well. Are you using explicit methods or implicit methods, or what do you use here, kind of?
Yeah, we are using implicit methods
Okay.
in Abacus. So it's very, it was very challenging at the beginning. So the reason we don't use explicit is because the model that we have is a viscoelastic model. So the time scale really matters in a simulation, because that is a physical material time scale we need to capture. So the storage time is, we set it to about 2 years. So you roll up the boom. In the simulation, we want to keep that for 2 years, and then we unroll the boom. So that is the simulation needs to take a physical time of 2 years. And if you look at explicit simulation, there is a certain time step that is the stable time step limit. And that's on the order of maybe, less than a second or something. So this simulation in explicit is going to take, incredibly, impossibly long time to do in explicit. So therefore we did not go, on the path of explicit. So we try to work, in implicit, and it was challenging because of convergence issues, but we were able to get it to work in the end. But there's implicit, and with the time dependence, there's another layer of complexity. So so I'm happy that we got it to work eventually.
Right, right. I mean, apart from the viscoelasticity, it's also the bifurcation and kind of the instability that leads to some kind of a nonlinear or a force displacement relation, right? So, how do you take care of those things?
Yeah. So I didn't show a more in detailed study on the bifurcation or the snapping instability study. So we actually use also Rick's analysis when we want to look at the fundamental behavior of the buckling under different sort of viscoelastic property of the tape spring. And so Rick's analysis is quite good. We are able to actually trace some of the bifurcation paths and snapping paths. So that what we found out is actually you can actually obtain multiple configurations, right? Multiple
Right.
stable configurations by varying the amount of storage time. So if you forward it to a localized buckle configuration, and then you keep that for some time, and then you release it temporarily, it's actually stable in that configuration. But it's over time it wants to go back, but it goes back very slowly. So you think about that as sort of a stable, but not really, because it actually it's not at an energy minimum. It wants to go back. But however, you can think about from a mechanical cycle or programming cycles to keep that as long as you want, or as short as you want, to get to different shapes. So we use sort of a Rick's analysis in for that mostly. But for this boom simulation we are doing for NASA, it was more of a design simulation we do for them. So there was just dynamic implicit with geometric nonlinearity. some damping involved, and they was able to get to the end. Just coiling and uncoiling, and understanding how much shape recovery it takes, so how long it takes to recover a shape. So we can now simulate all those things now.
I am just trying to understand all the details.
Yeah.
What you've done. So, are there any other questions?
Yeah,
Okay.
I have a question.
Hey, Manu, go ahead.
Yeah, hello, Dr. Kwai. I'm Manu from India. I'm a PhD student. I work mainly with time-dependent material behavior and stiffness degradation in them. So you showed mainly deployable structures in space involve polymers. I mean, they are made up of polymers, and the deformation are quite large. Do you see an effect of damage in continuum damage mechanics since the stiffness degradation on the effect, its effect on the actuation? And since you have shown a lot of experimental details on that.
Yeah. So there are definitely some damage. When we test composite, so we try to limit our strain to below 1% or below 2% at most throughout the structure when we bend it. But sometimes it does have damage. So the fibers break, and they typically break where I think my theory now is that they always start at the matrix rich region that damage, and then those are the weaker regions that they would appear. And that is what we observe in the experiment. So yeah, definitely there are some damage that happens. So we haven't really looked very closely, in the micro scale, if there are any sort of micro cracking in the matrix. We haven't done that, or fiber breakage in the micro. We haven't done that. But there is some work at Caltech by my advisor Sergio. He has an X-ray tomography, trying to look at these things, how the damage occurs fundamentally when you fold a composite.
Okay, thank you.
Okay. If there are no other questions, then maybe we can close the session. I think Kawai has already spent a lot of time, and I very much thank you, Kawai, for joining us today and for the really nice lecture and the discussions. I really enjoyed it. I mean, I cut out in the middle because of the internet, but I would go back to look at the parts that I missed. And we would also be adding it to the YouTube channel, and it will also be available on the website for somebody who missed any parts of the lecture. I think there was, I also posted the link in the chat if somebody is interested, or you can just go to the website and have a look at that. Thank you everybody for joining in today and really making the lecture interactive and nice. And once again, thanks Kawai for taking time and joining in. I hope you enjoyed as well, and look forward to talking to you.
Thank you for inviting. I enjoyed it. Thank you.
I have a lot of questions on the parts that I missed, but I'll come back to you on the email if it's okay.
Of course.
Thank you. See you, everybody.
Bye.